So I'm Jesse. We're talking about SelfTune, tuning for cluster managers, which it's by some authors from Microsoft Research and from regular Microsoft and Stony Brook University. And it was at NISD, the Networked Systems Design and Implementation Conference this year. The only reason why I really like giving presentations is so I can find old images to illustrate them. So I'm going to show you pictures of piano tuners. Like this one from Norman Rockwell, who is always great. So the problem that we're trying to solve is that cluster managers have lots of parameters. So this is like Kubernetes or whatever the software that is managing your cluster of services, and there are tuning parameters for scaling and memory and CPU management, and manually tuning all of these takes a lot of effort. You might not reach the optimal values, and you have to constantly update it because circumstances are changing. The workload is changing or something else is changing over time. There are lots of answers to this already, and the authors criticize the prior work by saying either that it doesn't reach the optimal values, or more importantly, that the existing heuristics don't learn quickly enough. They learn too slowly. So they present SelfTune, which it tunes in production. So there's no separate experimental phase because the experiments are expensive. So you need to find a local optimum quickly, because the period during which your production system is running with suboptimal parameters is costing you something. You're either spending too much money on hardware or you're violating your SLAs. And then the other really interesting thing about this paper is that it's got a pretty simple API for integrating SelfTune into your application. And unlike some of the other papers I've read about auto-tuning, this one actually gives you code examples and shows how convenient it actually is. So here is their code example for the API. So in this case, you've got some target utilization of 80% for some service or other, and you've got some tunable parameter, and this one's called update cycle. It's a time delta, and you declare its range as between 1 and 30 seconds, and the default is 5 seconds. You initialize a SelfTune instance, and you pass in one or more parameters that it can tune, and then you connect to a server. And this could either be one per individual machine or one per service or more centralized. I think it's up to you. And I think that that's actually a very interesting question about how it ought to be deployed, which I wish the paper talked more about. Anyway, so you then measure something, some reward function. And in this case, it's going to be how close is the current load to the optimal load, and then loop forever. So you check whether the current load is less than the optimal load. And in this particular case, the way this service works is that you generate some tokens and grant them to jobs. And that allows you to do more stuff, which will increase the load in order to raise it up closer to the optimal. And then you generate a GUID, and you ask SelfTune to give you its current guess what its tuned parameters and values should be. Then you implement it. In this case, the system does it by sleeping for some update cycle. That's the tunable parameter. In other systems, it could be that you scale the systems to a certain size, or whatever, you implement its advice. And then you calculate the reward function. In this case, you calculate the load, and you compare it to the optimum, and you tell SelfTune what the outcome was. When you do that, you pass back in that same GUID that you used with the predict call. This allows for asynchrony. I think that this is a really nice API feature because you could be on a different thread, a different machine, however you need to deploy this cycle, you have a method to allow SelfTune to correlate predictions with outcomes. And then you just loop forever. I thought that this was a little bit of a weird example of a tunable parameter, this update cycle thing. Like, wouldn't you want to measure load as frequently as possible if you were trying to reach a given optimum load? Under what circumstances do you like a system that performs better the less precisely you calculate the reward? I think it's weird if you've got a system that does better by waiting longer between measurements, that maybe there's something else going on here that ought to be, like, there's a design flaw. But regardless, the point here is that we've got an API example and it looks pretty nice. So this is the SelfTune API, and it gives you some idea of the SelfTune architecture, that you've got a server or servers, which could be on or separate from the ones that are providing the service. The learning algorithm itself is pluggable. And the only one thing that they discuss is called Bluefin, but in theory, it could be swapped in for anything else that supports that same API, which seems pretty straightforward. The Bluefin algorithm is gradient descent, quite straightforward. It loops forever on each round. It randomly perturbs each parameter up to some amount delta, which it calls the radius. Every parameter is perturbed within the same delta, so you need to do some sort of scaling to get that to make sense for parameters that have different domains, which they mention but don't give a lot of examples of. That creates a prediction. SelfTune waits for feedback. It receives the feedback. It estimates the gradient, and it updates the parameters according to the gradient in the direction of better reward, scaled by eta, which is the learning rate. In other gradient ascent algorithms that I've seen, delta would shrink over time as you more precisely approach the local optimum. In Bluefin, they don't. You always have the same distribution of random perturbations, and this is a good idea because it means that you don't get stuck in a range that was appropriate when you first started learning, but circumstances have now changed. So if you started learning during an idle period and then a spike comes, your new parameter values might need to be very different. And so it's good to preserve a fair amount of randomness so that you can discover the new optimum. The authors say that setting delta and eta requires some human insight or some experimentation. This is something that I wish they talked about more, because the emphasis is on how quickly and automatically SelfTune can find the optimum, but these parameters seem very important and they're not automatic. You have to figure out what they should be, and it doesn't tell you how to do that. In fact, it doesn't even tell you what the values were for any of their experiments, I think, or at least certainly not for the big final experiment in section 7. The authors also mentioned that if they measure the reward in just 2 cycles, that gives them a good estimate of the gradient, which is very surprising to me because it suggests that the space that they're moving in should always be planar. Otherwise, I don't see how 2 points is good enough. And so I would be curious to see whether more complex shapes are possible in the wild in real systems and how bluefin would react to those. The experiments. Section 5, there are 3 of them. In section 5, they tune the refresh rate of a workload manager that Microsoft uses to host Exchange Online and SharePoint. That was the code example that we saw. That's just one parameter. They kind of ramp up in complexity. Section 6 tunes 2 parameters. Those are the pre-warm and keep alive for a function as a service environment. And in section 6, they've got a nice discussion of what happens as the workload changes and how bluefin will update itself and catch up and find new optimal values. And then section 7 is the big one. They're tuning about 89 parameters for a Kubernetes managed network of 28 microservices. This is what I really wanted to see it do because this seems like a pretty realistic situation for medium to large company, and also that this is the kind of like intractable complexity that you want some kind of machine learning to get you out of. And so I wanted to see how well it would do. So that's what I'm going to concentrate on here. This image does not have a piano tuner, but it does have a piano. It's probably staged, but it's still a pretty awesome photo. So they've got an example social networking application with about 28 microservices. And where they got this social network app from is from a 2019 paper that introduced something called Death Star Bench, which is a suite of example microservice applications. This paper was written by the entire staff of Cornell University. Each author contributed 8 words. Actually, so to be fair, this was a big project. They wrote 5 or 6 complete microservice applications. Each had a couple of dozen microservices. They wanted to generate lots and lots of complexity for the purpose of figuring out what to do if you've got something like this. This is the AWS microservice interaction diagram from 2008. It's surely exponentially worse now. And we've seen diagrams like this for Uber and Twitter and all kinds of companies as well. So this kind of thing appears to be occurring more and more often in the wild, and we have to figure out how to manage them. So the Death Star paper is giving us some example applications that we can try to test management algorithms against. The one, their social network app is a lot simpler. They say it's got 36 microservices. SelfTune says it's got 28, somewhere in that ballpark. It's obviously a lot more tractable than AWS, but you can still see a lot of room for like chaos and dynamism and metastable failures and stuff, even in a system of this size. So that's what they used. They managed it with the Kubernetes vertical pod autoscaler. And they point some kind of workload generator at it and give it 15-minute bursts of activity. And I think it's completely idle before and after, although I'm not clear about that. They tried SelfTune and 3 competing optimizers. One is Bayesian optimization, and then there were two kinds of reinforcement learning methods. The parameters that they gave to SelfTune were 4 CPU-related Kubernetes autoscaling parameters, which govern kind of like how much history to look at, how quickly to scale up and down. And then they say about 85 parameters for the 28 microservices. Later on, by the way, they say that only a few of these really matter, but obviously you don't know that a priori, so it's good to give them all to SelfTune. Again, they don't mention how they chose delta and eta, which I found frustrating. And then an interesting thing is that the optimizers themselves, they don't scale up and down. They just tell Kubernetes how quickly to scale up and down. So there's kind of, you could almost think of this as hyperparameter optimization, and then delta and eta are hyperparameters. And during the experiment, they go for 50 rounds, which means 50 bursts of 15 minutes of load, so that they all get an equal opportunity to learn the optimum parameters. So in their evaluation of the work, they said that Bluefin achieved the best throughput of all of them. Just once, I want to see a paper that says we were pretty good, but the competition was better. In this case, they only beat the next best competitor by 2.2%, although they were much, much better than just whatever, accepting the defaults. The big win here is, they tell Kubernetes to scale up rapidly during the peak and scale down rapidly afterwards, which is good because they have a spiky workload, but apparently they weren't much better at those parameters than Bayesian was. But the big win here is that Bluefin learns fast. It converges after only 8 samples, whereas others take 3 to 5 times more samples before achieving their best values. And you can see that this really matters, especially if the environment is changing. You want to be able to re-optimize pretty quickly because this is in production. You are violating SLAs or risking outages or wasting money while you are converging. So converging fast is good. My evaluation, compared to some other papers that I've read recently, I really liked how they actually showed code. They showed how, if you wanted to use this, you would integrate your code with their API, and the API looks nice. And the experiments are extremely thorough compared to other papers like this that I've read. I wish they talked more about delta and eta. And I kept wondering whether the space was more complex in real life than they thought it was, whether 8 rounds maybe gets you to optimum in the section 7 experiment, but what if there's some other optimum somewhere else in a much more complex system? Would you be able to find it? And particularly if the environment changes such that maybe you do find a global maximum the first time around, and then the workload changes such that there is another global maximum far away. Would you ever find it with this sort of local hill climbing algorithm? I don't know. And then I also wonder how large the scope of each of the SelfTune instances ought to be. If you've got a network of services, what are the trade-offs between local instances of SelfTune versus one global instance? Definitely, say, in the circuit breaker paper that I think we read, and in the metastable failure literature that kind of orbits around Alexei, it seems like the wider you can see, the less likely you are to have emergent bad behavior like bottleneck shifting or oscillation. So The paper sort of seems to advocate just putting an instance of SelfTune on one service or even on a single machine, but then it seems to me that there might be an oscillation of parameter choices among instances of SelfTune that basically cause them to shift the bottleneck around between them over time and maybe start oscillating. So I would wonder whether a global instance would be better, but then I also wonder whether a global instance might be overwhelmed by the complexity. So I'm curious what the trade-offs are there. And that's all that I have to say about this paper. Thank you.